Hey everybody, I'm Adam, and I'm so excited to be here and to talk to you about Sketchpad, the first computer program that had a graphical user interface. Well, let's back up. So in 1962, if you would ask somebody what the user interface was to a computer, it was a human being who would take your stack of punched cards or other input, and their response would be, come back tomorrow and get the answers. So it's kind of amazing and hard to believe that also in 1962, there is this kind of a computer interface in exactly one place in the world. In MIT Lincoln Labs, we can see somebody using a piece of software that is recognizably software. There's a live screen showing the state of some process. There's a pointing device where they can directly interact with things on the screen. And there's buttons and commands to take actions on it. The program that you're looking at is called Sketchpad. And it was created by Ivan Sutherland, who is a PhD student, as part of his dissertation. And it's a piece of software that there was sort of nothing like it before and not anything better than it for 10 or 15 years. In today's talk, I want to pass on my excitement about Sketchpad and hopefully get some other people who are excited about it. I want to show you a live demo of what Sketchpad could do. I want to talk to you about some lessons I learned while making a sort of new version of Sketchpad that will run in a web browser so you can actually play with it. And I want to talk about why it's worthwhile to study old programs, especially old UIs. So let's start with a demo. Here's my little instance of Sketchpad running in the browser. And Sketchpad was a program for making precise diagrams, things that needed to be mathematically correct or that would be difficult to do by hand. You'd have to measure and calculate in advance or use drafting tools. But Sketchpad's goal was to make it much easier to generate those kind of precise drawings. If I can see my mouse in the sunlight. Cool. All right, so I'm gonna draw a rivet, and I'm just gonna start by drawing some lines here. And I'm gonna draw them pretty imprecisely because I don't have to draw them precisely because I have a computer. So what I can now do is ask the computer to make these lines perpendicular to each other, and it'll just kind of nudge around the points until it does that, which is cool. Now I need to find the center point of this nice rectangle that the computer has made for me, which I can do by drawing the diagonals. And now I want to make the head of the rivet, which should be an arc centered on this middle point and going out to this end of it. And now you can see, I didn't calculate this in advance. I've been really sloppy. I really want this arc to end all the way over here. So I'm just gonna tell the computer, hey, I want the arc to end all the way over here. I'm gonna kind of nudge everything around until all the nice mathematical properties of my diagram work. Now I have a part that I'm trying to build that actually needs a rivet in it. So I'm gonna come to my other picture, and now I'm gonna make a new instance of my rivet, and I can rotate it. What I really need to do is zoom it smaller. And so now I can use my first drawing as a symbol inside another drawing. So I want to just pause there to say, it's kind of amazing that you would invent the very first GUI ever and not just do like MS Paint. You'd actually you'd do a constraint solver, and you'd invent like a component and instance system. It's a really cool and powerful program. So let's talk about what it did take to implement this and what I had to recreate. So in memory, we're going to represent our drawing as a bunch of individual blocks, chunks, pretty much like structs, but Sutherland called them blocks. So we've got a point block, and it knows its x and y coordinates. We've got a line, and we've got a circle. And we're going to imagine that this line and circle depend on this point. It's one of the coordinates that they use. So he invented a data structure that he called a hen and chickens. We today would just call it a ring, that connects all the items in some children that share the same relationship to some parent. So this lets you say, if you're doing something with the point, this lets you walk through to all the shapes that depend on that point. If you're doing something with the line and you need to know its start point, you can walk through the ring to find that. This is an efficient way to represent that. Now you get to doing some operations. Let's say the user wants to delete the point, and so we also need to delete the line and delete the circle. Well, you can start to write that code and you run into a problem, which is that in this ring, you have different types of things. So how do you know which operation to apply the way to delete a line instead of the way to delete a circle? The first version of this program had the equivalent of a big like lookup table and inline branching, and that got annoying as he added more stuff. So Ivan Solove invented this idea he called generic blocks, where he would connect each concrete point in the drawing to this generic block called the points block that has another ring that goes to all the points. And similarly for, line is connected to a lines block, circle is connected to a circles block. So now when you want to write code that deletes a point, you can say, go to each shape and just don't worry about what type of thing it is. Just ask its parent how you delete a shape like that. This diagram isn't presented exactly in the dissertation. It's not this clear if you read it yourself, but if this looks like object-oriented programming and he just like invented it as an offshoot of his other thing he was trying to do, that is in fact historically true. Alan Kay has said that it was reading this paper along with one other in 1966 that gave him the idea for what would become object-oriented programming and Smalltalk. Again, just sort of like on the side of this thing that he's trying to do. He also became, I think, the world's first UI programmer to get kind of lazy and want to refactor everything every time he added a new feature. So he says that he's become reluctant to write any specific programs for any specific jobs, because you could just sort of keep rearranging the system until it's really easy to do. It also raises one more question. If a circle is connected to a parent that's the circles block, what happens if we keep going up that chain? So he invented the world's first inheritance hierarchy. The circles block is connected to a thing called topos, which is like all the different shape types. And that's connected to universe, which is everything in the system. It's like a basic object. And then he asked a theoretical question, which is, well, universe needs a type too. We shouldn't just have one special thing that doesn't have a type. And so he speculated it really ought to be the case that you could just keep going infinitely up and create more and more abstract things. Very generously of him, he decided not to do this. So in this dissertation in which he invented so many other things, he left at least one thing for later people to come back and invent. And if this looks like meta objects in Ruby or in Common Lisp object system, he basically had that idea and then was like, maybe somebody else can do that. A fun aside, his PhD advisor was Claude Shannon, who had invented information theory and the fundamental basis of electrical circuits in his master's thesis. And people made him come back and do a PhD dissertation as well. But he was a little picky about his graduate students. And so he came to see a live demo of Sketchpad in an early state. And his student had invented GUIs, had invented object-oriented programming, had this cool thing. And he was like, why doesn't it have circles? I really want it to have circles. And Sutherland explained to him, nobody has an algorithm for calculating the points on a circle fast enough to be in this program. And Shannon apparently was like, that's a bullshit excuse, figure it out. So Sutherland had to go work with mathematicians to find a new algorithm so that he could draw circles so that his advisor would come actually watch the demo and pay attention. So if you're a graduate student, hug your advisor. If you're a UI engineer and you've had a stakeholder come and just be like, could you just add this one feature? It should be pretty easy. You're proud of a proud line from the very beginning. There's one other thing, one other fun detail here. When you see the original videos and screenshots of Sketchpad, the lines have this warm, fuzzy impreciseness to them. And there's a reason for that. He was using a really old CRT, and moving the laser for the CRT was really slow, and each pixel after it lit up would take a while to fade back. And those two things together meant that if you drew the picture kind of like each pixel in one line and then each pixel in another line, you'd get this effect where different parts of the screen were brighter and dimmer, and you'd get a really weird strobing effect, and it hurt everybody's brains, and they couldn't use the program. I'm not going to show it live, but if you just sort of imagine this, but then rotating at 60 hertz, it's really painful. So he invented an algorithm he called twinkling, which would draw the points in the picture in a sort of pseudo-randomized order. And it gives it this effect of it's less precise, but it's warm and fuzzy. It feels like old analog electrical equipment. I love it. So I, in my recreation, made an HTML canvas element API that would kind of draw this slowly and fuzzily. And it's, on the one sense, a complete waste of time. And on the other hand, it makes me very happy. So I want to leave you with some thoughts on why we should study old UIs. One professor taught Sketchpad in an intro course, and some students came up afterwards and said, what's so cool about that? Isn't that just what computers are? But they're not. Everything about the world of computing we work in is contingent. It's a decision that somebody made. They might have made it right or wrong. The ones that survived to today might have been the good ones or the bad ones. It's worth studying the old things to find out which historical mistakes or which historical precedents are worth revisiting. Finally, I love the complete optimism of people who are doing something for the first time. This is one of the section headings in Sutherland's dissertation, and I'm afraid of needles, but if I were going to get a tattoo, this is what I get a tattoo of. The as yet undreamt of things that will be displayed. Even today, 61 years later, there are still undreamt of things that are yet to be displayed. And that's what I like doing. Thank you.